lengths of monitoring as well, which I can talk about towards the end. So when we're doing deep learning methods or any type of machine learning methods, you're going to have your training set, your validation, and then your test set. And so here's going to be the results of our held out test set when we look at how our model's performing. So we can compare it to the single task AF where we don't incorporate signal quality, and then we can look at what we end up selecting, which is going to be that multitasking with the pre-training from the convolutional denoising autoencoder. We see that the sensitivity rates they just go so high when we incorporate that signal quality, which makes sense because the signal quality is giving us some information on whether or not we're able to correctly classify an AF event. So it makes sense that our sensitivity is going to increase greatly. So we already had a good faith that when we talk about incorporating both signal quality and AF, it would be a strong basis for AF classification. Another thing we wanted to look at when we're talking about not only single task is, again, the use of pre-training. So here's going to be the set of experiments where we chose to include pre-training with those convolutional denoising autoencoders, and when we not. And when, again, we do see that that benefit helps with using those pre-trained encoder regions and those pre-trained weights. Another thing, let's see, actually, let's go here. Okay, so when anyone shows kind of high discriminatory power on a test set, it's always, I say always take it with caveat, because that data set is coming from that same population distribution that the training set was. So the test set is coming from that same distribution as the training set. But to be able to transfer those results to a completely different population is going to be much more difficult, and it's going to be more indicative of how well the model will perform kind of out in the wild. And so that's what we really wanted to highlight and test. So we decided, I think it was 1.5 years after I created the algorithm, was to include and start collecting a completely external data set. So this is beyond just the ones that we saw in hospital. In this situation, I wanted to say, you know, in a controlled setting in the hospital where I collected the initial data for training and testing, it was a controlled environment. But in reality, I want this algorithm out on people who are walking around. So we need to be able to test it on those people. So we consented 15 individuals in what we end up denoting as our ambulatory cohort. We broke those windows into 25 seconds, which resulted to around 20,000 windows. And of those windows, we had around 2,000 AF events that were a gold standard. It's important to note that we sent them home with different devices that were of a different generation of Samsung. We also sent them home with the Zio patch, which essentially is a patch that is a 1-lead ECG that monitors your heart. So we use that as a gold standard. And again, we sent them home for a week and asked them to kind of go around their general lives. At the time where we were incorporating this external data set, there was another benchmark data set that came out that had this type of signals. They were all normals, but we decided to include this in our external validation to see how our model would work on different devices and also in different settings. Okay, so these are going to be the results from our external data set. So in the publicly available data set, we had, again, it was all normal. So we didn't have any situations of false positives. So the model correctly classified all of the windows from the normal public data set correctly. When it came to the ambulatory monitoring, it's important to note that we monitored 15 people, but out of those 15 people, only 4 of them actually had events. Like I said, AF is latent, so some individuals may not have it, but it also can come and go. And we only monitor them for a week because we had limited, resources to be able to monitor them for months at a time. So within that week, we were able to catch 4 out of the 11 that had actual events. And here are our sensitivity, specificity. false positive rates, and F1 score. So these are all ways and all metrics that we use to evaluate a classifier and how well it's working. So this kind of gave us a really kind of high hopes in terms of how this type of algorithm would perform out in the wild. We had very low false positive rates, and we had faith that this type of algorithm would work quite well in an everyday environment for high-risk populations. Again, I'm highlighting the low false positive rate. And some people like to see the numbers. So we classified all 4 of them correctly. So all 4 of the ones that had an event, we caught it, and we were able to classify 925 episodes out of 929 correctly. So we only missed 4. So to summarize, this is BeatBeat. It's a multitask learning for cardiac rhythm detection and wearable devices. We built this method by a combination of these 4 crucial aspects by incorporating convolutional denoising autoencoders, the benefits of using simulated data sets, especially in a medical setting where data is highly limited, incorporating 2 tasks that are going to be similar are actually beneficial, especially when it comes to these deep learning models, and then taking it beyond just your test set, incorporating an external prospective validation study is going to be critical to kind of get a true estimate of really how well your model's working beyond your test set, which is going to originate from that same training set distribution. And so and really quickly, the data is public, the model's public. So if you ever are interested, you can look it up and download it yourself and play around with it. It was really kind of a goal for me when I started this project to make sure that the data we collected and the models I trained would be available for everyone, because as you guys know, there's lots of companies that are doing this type of work, but as scientists, this data is sometimes not really available. So what can I do as a scientist to kind of promote reproducible science, but also more scientists to get interested in this field would be to release the data. So we did that. So if you guys are interested, that's available within the publication as well. So I'm going to get to some of the questions that were sent over to me, and then I'll answer them, and then we can have more conversations about my other part of the PhD, about this work or what I'm doing now, because it's still very within the same field. Okay, so one of the first questions was, out of all the classification models trained with similar hyperparameters, what was taken into consideration to objectively compare them? So those were the metrics in terms of sensitivity, specificity, F1 scores. All of those metrics we use were the same for every method. And those metrics are going to be some, gold standards that the industry uses, but also clinicians use as well. And so it's really critical that whenever you're using some type of machine learning method, that those metrics are the same. Did you consider the weight transfer should be applied regularly when working with the CNN? Or should it be used only in similar conditions as the paper mentioned? So I think it's something that you kind of have to test out. In our situation, it was extremely helpful. In most cases, if the data is somewhat similar, it will also be helpful. That's kind of what, especially in the language models, the pre-trained, BERTs that you can download and then you fine tune on your data, it tends to help learning significantly. And so this is very similar to that, where I had a huge corpus of simulated data. I trained it on there, and then I fine-tuned those weights on that real collected data set, and I saw that benefit. So that tends to be the case when it comes to most data sets. So if you have the ability to kind of use pre-trained models or pre-train a model itself on a somewhat similar task, it may be beneficial to you. Okay, so the next one is the paper mentions the performance of DeepBeat is improved through convolutional denoising autoencoders. I would like to know how the convolutional denoising autoencoder model was tuned. Specifically, how was the latent space chosen? I would imagine that the cardinally latent space. Okay, so when we were talking about the convolutional denoising autoencoder, we tuned that to have essentially the lowest mean square error. So we just wanted the error to be the lowest in that data set when it was estimating, you know, the true clean signal when you put the noisy signal in. There is when I was kind of working on this part of the project, there wasn't good standards in terms of pre-training on how long you should pre-train. When do you stop pre-training? Kind of when does that, when do the benefits kind of like stop working? So I found that I trained it until I found the lowest mean squared error, and then I set those weights, and those are the weights I used. I think it's definitely something to be said that would be a really interesting kind of research question on, you know, at what stages does that improvement really start benefiting you in the long run? Could there be some more interesting choices you could make to see that benefit trade-off? But mine was pretty standard in terms of what I end up choosing to do. Okay, so next question is, this is about using skip connections between the encoder and the decoder, and talking about the UMET model as kind of inspired this question. So that is a good idea. So UNet is going to be a model that's very popularly used for segmentation tasks. So if in the window I wanted to kind of get the start and end positions of AF, this would be a great model for me to kind of segment that signal into different parts. I think it's definitely possible. In our situations, we chose not to use it. I think it would be a really interesting option, but yeah, we just chose not to in our case. The second to last one, what are the reasons to use specified window length of 25 seconds? So we actually looked at different time lengths. We looked at 15 seconds, 25, and 45. And we have to think about also use case. As a scientist, I never want to create something that's not useful. It may be, you know, the greatest idea ever, but if it's not useful, it's not going to be applicable. And so when I was designing this approach, it's important to understand what your limitations are, especially when you're working with any device. These devices do not flash on continuously forever. And that's because of battery, you know. So in most cases, when I was working with Samsung and their engineers, we talked extensively about battery. And so for the most part, these devices will flash on for around 15 to 45 seconds. Just because if it was on continuously, it would drain this battery and then I'd have to charge it, you know, every hour. So I wanted to create an algorithm that would seamlessly integrate into what is already done. I'm not a battery scientist, so in terms of, you know, I had to work within the limitations that was possible. So we use 25 because that tends to be a long enough time for us to get a good perspective on if AF is present, and also work within the realms of our battery limitations. And last question is, can you explain a little bit further about class imbalance and the use of mean harmonic precision and recall for AF detection and why it's better than accuracy? This is a great question, and I think this is a question that a lot of individuals who are new to the space tend to not address properly. So what I like to do is, the way I like to think about it is, a lot of times people will just look at accuracy. And so accuracy, although is great, in some cases, it's not going to be the best metric. So in a case where, let's say I have 100 samples of something, but only one of them, let's say I'm just using cancer versus non-cancer. I have 100 cases and I want to detect cancer. All of 99 of them are going to be normal, and one of them is going to be cancer. And let's say my classifier was to detect, you know, whether that cancer is present. Well, if I'm just always calling a normal, it's going to be the accuracy is going to be 99%. And so the scientist, I'd be like, wow, I'm so smart. I created an algorithm that's 90% accurate. When in reality, my algorithm is not working at all. It's not able to classify that one instance. And so if you went off